Good afternoon, ladies and gentlemen. Thanks for tuning in. It's a great pleasure to welcome you all to our second webinar in the Rain Enhancement Hub series, hosted by the National Center of Meteorology and organized by the UAE Research Program for Rain Enhancement Science. My name is Yusuf Wehbi. I'm a program officer for the UAE REP, and I'll be moderating today's webinar. First off, I wanted to give a quick recap on our first webinar we hosted back in May, where we discussed the background and some of the drivers for rainfall enhancement research and operational cloud seeding. We specifically discussed the UAE's efforts in both fundamental and applied research in the field through its operational cloud seeding program, as well as its pioneering research conducted by our awarded projects. Inspired by the saying, to understand the present, we must first understand the past. And today's webinar will take a glimpse back in time to better understand the variability of rainfall throughout the past decades, specifically over the UAE, but also over the broader regional scale of the Arabian Peninsula. Joining me today to share their insights on this topic are two very distinguished speakers. Professor Taha Awarda, Canada Research Chair in Statistical Hydroclimatology at the Canadian National Institute of Scientific Research, as well as Dr. Diana Francis, Senior Scientist and the head of the Environmental and Geophysical Sciences Lab at Khalifa University here in Abu Dhabi. A couple of housekeeping points just before I hand over to the speakers to start their presentations. For our audience, please go ahead and type in your questions at any time using the chat box. We'll address your questions during the Q&A session after both presenters have completed. I now welcome Professor Taha Awarda to give his presentation on rainfall trends over the UAE.
Thanks, Dr. Yusuf. Well, thanks everybody for being with us today. So I'm going to be talking about the rainfall evolution, basically the evolution of the rainfall regime in the UAE. And we're going to make sure, before I start, I want to make sure that we agree on certain definitions so that we speak the same language. So we talk often about climate change and climate variability. I want to make sure we agree on the difference between the two. Climate change is the long-term trend over a very long period of time, say 30, 40 years. It's the long-term that we observe in the series. Climate variability is the fluctuation around that overall trend. So it's the difference of the series with that trend. It seems fairly easy, but we'll see that often it's not easy to separate the two. Climate change, I believe everybody knows the concept. The radiation that is absorbed by the Earth, part of it is reflected. Greenhouse gases come and trap part of the reflected radiation. So the more greenhouse gases, the warmer the temperature of the atmosphere and the Earth. Climate variability is a bit more complex. So when we look at our climate, it's fairly controlled by what happens in the oceans. Oceans drive actually our climate. And oceans move huge amounts of water with a huge amount of energy. And if we look at this current over here, for instance, going from the South Atlantic to the North Atlantic, it's going to go through the Caribbean region, create all the havoc that we know every year. And then it's going to move to the east and go towards Europe, where all the heat is released. Then the current that's going to be going down near North America is going to be a cold current. So if we look at two cities at the same latitude, if we look at the city of Quebec here and the city of Paris here, they are the same latitude, but when it's minus 25 in Quebec, it's plus 15 in Paris. That difference in temperature is mainly due to what these currents are doing. So the impact is huge, okay? If the current didn't go to the right and stayed near North America, then the heat would be released here and Quebec would be warmer than France, okay? So that illustrates a little bit the impact of these currents. Now the problem is that they're not regular. There are years where they're stronger than others and they would transport a bigger amount of heat, a larger amount. So we would have a warmer year or a colder year. It's going to influence other variables such as precipitation. So this creates interannual variability, and to try to monitor and measure this variability, we're looking at the intensity of these currents. So we're looking usually at the difference of pressure or temperature between 2 points on the path of this current. And by doing that difference, we have a measure of the intensity of the signal, because water fluids will move usually from higher pressure to lower pressure. So that would give us an indicator. So we developed a whole bunch of indices that reflect what's happening in different oceans. And those indices now represent predictors of our climate, because if we know the intensity of this signal, we have an idea about how hot or how cold the next season is going to be. There are a number of indices. One that influences what happens in the UAE is the Indian Ocean dipole, and in which we're measuring the anomaly between the temperature in the eastern and western Indian Ocean. And that would be an indicator of how strong the signal is going to be. There are a whole bunch of other indices that influence the UAE, the Southern Oscillation Index, even the Mediterranean and the North Atlantic. So the signal gets fairly complex because these indices don't have the same phase. So sometimes one is in a positive high phase, one is in the lower phase, and then it may be high phase with high phase, okay? So the response of our climate to these indices gets fairly nonlinear, and we need sophisticated approaches to read what's happening. As I said, it seems like fairly automatic definition, climate change and climate variability, but sometimes the signals get mixed up. So if I look here at what's happening at the Koulikoro station on the Niger River in Africa, I worked on this a fairly long time ago. And when we worked with this series, we see that from the early 1950s all the way to 1990, there was a significant decrease in the stream flow in Koulikoro station. And it would have been easy to assume that this is a climate change signal after it lasted for more than 40 years. So it's going to keep decreasing and we can extrapolate. Well, what happened is that starting 1990, stream flow started increasing again. So this decrease that we observed over a 40-year period is not climate change, it's actually climate variability. It's part of the fluctuations. Some of these indices have a multi-decadal signal. So the fluctuations might last for several decades. That's why I'm saying that we need to be careful when we try to separate climate change and climate variability signals. So let's look at what's happening with precipitation in the UAE. We all know that the UAE is a dry environment, so every drop of water matters, not just for consumption and for groundwater recharge, but for environmental purposes also. We ended up working with 6 stations, very good stations that are mainly located in the main airports in the UAE. We looked at a number of variables that are extracted from the daily rainfall series, the total annual and monthly rainfall. Then we look also at the maxima, the annual and the monthly maxima. So we're interested in the total amount of water for supply purposes mainly, and we're looking at the maxima also as extreme events that can cause damage. We're also looking at the number of rainy days per year and per month. So we're considering the year as starting on September 1st rather than the calendar year. It's a hydrological year. We just try not to split the winter season in 2. When we do trend analysis, we use the modified Mann-Kendall test. Mann-Kendall test is a test that identifies trends in a series, and the modified version takes into consideration autocorrelation. Because when there is a correlation in the series, we may mistake that correlation for a trend. So we need to do a correction to take into consideration the correlation. And when we do the trend analysis, for all the variables, total rainfall, max, and number of rainy days, for all stations, the 6 stations of the UAE, annual series, and all the monthly series. When we do this, we observe a decreasing trend everywhere. So it seems as if rainfall is decreasing in the UAE systematically everywhere and for all variables. But when we zoom in on the months of November and December, we see a lot of positive trends. So something is happening here differently from the rest of the year. But overall, we can tell that, yeah, it seems that there is a decreasing trend. If we look at the series, here we have the total annual rainfall, and we plot the trend lines. They're everywhere negative. So it's a decreasing trend everywhere, which confirms what the test is telling us. This is the maximum rainfall, and this is the number of rainy days. It's the same thing everywhere. So a lot of people say that, oh, rainfall is decreasing in the whole peninsula, and the first look seems to indicate that they may be right. But we need to go further. So we do a Bayesian change point detection procedure, where we're trying to detect points in the series where there seems to have been a shift, a change in the direction of the trends. And when we do this, for all stations, all variables, we see that there is something that's happening around 1999. Around 1999, there has been a change, a shift in the series. When we integrate that in the analysis, we see that now, for all variables and all stations, what we observe is that we have an increasing trend. So rainfall, here the number of rainy days, for instance, is increasing throughout the series, but with a shift around 1999, a big drop. So you're going to say, maybe for Al Ain we have a decreasing trend. No, that's just because the series is short here. It's the same portion than this part of the series. If we had a longer series in Al Ain, we would observe the same trend. Okay, so the overall trend is increasing with a big drop, a shift in 1999. What's that due to? So to summarize, what we thought originally as to be an decreasing trend in the series is actually an increasing trend with a drop, a shift around 1999. But if we go and we look at the timing of the events, what I'm putting here is in blue all the annual maxima before 1999, and in red all the maxima after 1999. This is for Abu Dhabi Airport. And then I'm combining all stations together. And what we see is that before 1999, the extreme events, the annual maxima, are systematically occurring in February, March, even April. While after 1999, they're systematically occurring in December, January. So this decrease in the magnitude, this shift that we observed around 1999, is also associated to a change in the timing of the extreme events. They're occurring earlier. Okay? So what we ended up doing is a whole bunch of analyses to try to understand what explains this drop and this change in the timing of the extreme events. And if I show you here a number of climate oscillation indices, these indices that I talked about at the beginning of the presentation, like the Southern Oscillation Index, we see that they all go through a change of phase around 1999. Okay? So here what I'm presenting is the cumulative sum of the index. And what we see is that around 1999, these indices go through a change in their phase. They go from a positive to a negative phase, or from a negative to a positive phase. And that has a direct impact on precipitation. So variability in the series that we have is taking place at a very low frequency. And we have observed in the whole series just one change of phase in these dominant indices, and that has been the main driver. The overall trend is positive, and the change of phase of the indices resulted in that shifting point around 1999. Based on this, we can go now and develop models. Once we develop the correlation between the indices and precipitation, the total, the maxima, the number of rainy days, for each one of these variables, we can build these nonlinear predictive models that tell us, based on the link with these indices and their impact on the response for each station, and integrating also the trend signal that we're observing, here is how our total annual rainfall or our maximum rainfall evolve as a function of these indices and trend, so time. So here I'm showing a number of indices and their impact on precipitation. This type of model is now becoming more and more used in a number of countries. We're building predictive models that say, given the impact of this and that index on our climate in this region. And given the overall trend that's being observed, here is what we're expecting for this year. So a few months ahead of the winter season, we would say this year we expect to have more rain, or the total amount of rain is going to be approximately average, but it's all going to be concentrated in a few events. So we're going to have extreme events, but that's not going to affect the total amount of rainfall, or we may have a very dry year. If all the indices that impact our climate are on the negative phases, or the phases where they impact negatively precipitation, then this is going to be an extremely dry year. So these are the type of models that we're working with now that allow us to do the long-term prediction of what's happening with precipitation. But this is not going to help us with short-term prediction. This is not going to help us to forecast like what's going to be happening with rainfall in the next 2 or 3 or 7 days. Okay, it's more a seasonal forecast to annual forecast. We can even develop forecasts that are 2-3 years ahead of time, but they are of lower quality with these type of models. I'm going to stop here, and I hope we're going to have some good questions. Thank you.
Well, thanks a lot, Dr. Taha, for this insightful presentation. We'll hold, of course, we do have some questions, but we'll hold them for after Dr. Diana finishes her presentation. I also wanted to mention that the paper that Professor Taha quoted in his presentation has actually formed the basis for a lot of further research in this field. It's in the Journal of Hydrology. We can talk more in the details during the Q&A. I now welcome Dr. Diana Francis, Senior Scientist and the Head of Environmental and Geophysical Sciences Lab at Khalifa University, to give her presentation now on the bigger picture of rainfall and climatological trends over the regional scale of the Arabian Peninsula.
Thank you so much, Dr. Youssef. I'm very pleased to be part of this webinar, and I would like to thank UAE and NCM for organizing this series of webinar under the Rain Enhancement Hub. So today I would like to talk with you about precipitation and weather trends in the Arabian Peninsula, with a focus on extreme convective events and rainfall. So first of all, I would like to introduce what is a convective system. As many of you may know, in the tropics and subtropics, so these are these red band and yellow band here on the globe, rain does not come from storms as we know them in the mid and higher latitudes, normally with associated cyclones, but it comes from convective cells, which develop during the wet season. So this kind of cells is the main feature that brings rain to these regions. So why is that? Because a tropical climate has its specific atmospheric patterns. For example, if we look at the African continent, during summer we observe the development of a heat low. It's a thermal low in response to the extreme heat by the sun during summer. So this heat low, once it develops during summer, it drives toward the cold and moist flow from the surrounding ocean. So now I'm going to play animation to show you better how things work during the wet season in tropical regions. So you can see here, for example, the deepening of the thermal low due to the heat by the sun, and the dry and hot northeasterly flow, which is meeting with the cold and moist southwesterly flow. Between these two, we have the intertropical front, or the intertropical discontinuity region. It's a region of very strong convergence, because as you can see, it's the region where two opposing winds are meeting. So this convergence is actually the trigger for the development of convection in tropical regions. So this is again the animation on this. And now, so what makes a convective system? A convective system is actually several organized convective cells that develops over this region, as we said, during summer, and they move as a whole system. So we call it a convective system. So once again, these convective cells are the result of extreme heat first, then availability of water vapor, which is also made available by evaporation during summer from the ocean, and the low-level conversions. Now, as we all know, the Arabian Peninsula is located actually in these zones, in the tropics and subtropics. So it has also this type of climate characteristics. And what I would like to highlight with you today is, or try to answer, is some of these questions. For example, when the convective systems occur and how long they last. What are the trigger mechanisms for their occurrence? And what are their impacts? Why we are interested in investigating them? What are the trends? What are the challenging in studying MCS? MCS is the abbreviation for mesoscale convective systems. Are, for example, accounted for in global models? And what is the main remaining scientific questions? So this we can also discuss during the Q&A session after my talk. So if we start by looking to their occurrence on an annual basis, we can see here, for example, a study recently published by Nelly et al. In Atmospheric Research. It covered the period between 2000 and 2020. And in this study, we identified all the mesoscale convective system occurring over the South Arabian Peninsula. And here we can see we have a peak in occurrence of mesoscale convective systems during spring and another peak during summer. It's very important to bear in mind that the type of this mesoscale convective system is different, because the ones that occur during spring are of more larger scale, whereas those developing during summer are more locally. So they develop locally over the UAE and surrounding countries. So this is on an annual basis. Just the message is that we have a peak in spring. We have a lot of convective activity during this season and also during summer. Some also occur during the winter and fall. Now, if we look at the daily basis, which is the favorable time for their occurrence, we found that the most favorable hours during the day for MCS occurrence is late afternoons to evenings, which is expected somehow due to the accumulation of the water vapor in the atmosphere during the day. And now, if we wanted also to identify what are the drivers that promote the formation and occurrence of mesoscale convective systems over our region. So here I'm showing to the left up panel is satellite imagery of clouds in the infrared. And in these images, you can see the clouds and the convective clouds appearing in blue. And just below it, we have the radar observations at the ground. You can see how the cells appear in these observations as well. This case occurred in April 2019. We noticed that for all these cases, the common two features that are present are especially an intrusion of mid-latitude trough that will trigger the convection at the border here. And we have an equator-ward displacement of the subtropical jet that also favors the development of convection and its drift toward the UAE and southern peninsula. Now, this was during spring. As I said, different mechanisms play a role in the development of spring convection and summer convection. How about summer? So during summer, we have to account for different conditions at different altitudes. So if you look at it as this is so the altitude, so above the surface and up. At the surface, normally if we have orography, we can trigger convection during summer. That's why most of the convection over the UAE occur near the Al-Hajar mountain here. And if we go above the surface, we have some conditions to be met at low level, especially a strong temperature gradient between land and sea, We need to have also a strong moisture gradient between land and sea. And the convergence is always important to trigger the convection. At upper level, if we have a trough, that also can trigger the convection during summertime. Now, if we look, for example, in real data, what is the picture that we get? Here again, at low level, we have the map of temperature, map of 2-meter water vapor mixing ratio. And at upper level, we have the 500 hectopascal geopotential height. So in the temperature map, you can see we identified that the gradient need to be higher than 10 degrees Celsius. And this is the ITD here over our region during summer. It can go north to the coastal line in some cases. For the condition on the water vapor, we need to have a gradient that is above 10 gram per kilogram. And regarding the trough, we can identify it in this color here at 500 hectopascal geopotential. And this is the convection that can result during summer from this setup of atmospheric patterns. So here, these are the cells that developed, for example, on this day. You can see the convective cells and the whole system moving as one. Okay, so now one can think why, for example, it's important to study convective systems. They have these systems have many applications. One of them is they generate a massive dust storms. Why is that? I'm sure whoever is living here or in any tropical region noticed, for example, that before the rain, most of the time we have some dust present in the air. So the atmosphere is very dirty, visibility is low, and then after that comes the rain. This because when these convective systems develop, due to the convection here, we have generation of downdraft. Downdrafts are very strong current with a density very different from the surrounding atmosphere, and they form a cold pool. So this cold pool, because of the density, it goes near the ground, and it's associated with a very high wind speed and turbulent mixing. So these winds here generate emission of dust if, of course, they occur over a desertic area. This is, for example, a convective system that occurred over West Africa, and we can see very clearly the dusty cold pool here and the clouds on top of it. It's very important to forecast this mesoscale convective system for this because of the impact on the daily life from disturbing the traffic or visibility or health issues as well. But also, mesoscale convective systems can cause flooding. I'm sure many of you have already experienced this here in the UAE. This is, for example, for a case in March 2016, where the city looked like this on that day when a convective system developed over this region, as we can see here from satellite imagery. So now, what are the trends in the extreme convective system over the Arabian Peninsula? These two slides are focused only on the spring rain, and it's again from the Nelly et al. 2021, which covered a period of 21 years. And we observed an increasing trend in the duration of mesoscale convective systems, meaning how long they last once they form. And also we observed an increase in the rainfall that is resulting from these mesoscale convective systems over this period of interest. And now these trends that we observed here over the Arabian Peninsula were also observed over the Great Plains in the US. And many scientists associate them to the global warming because of few factors. I can cite some of them now and later discuss more in the Q&A session. You know, for example, that a warmer atmosphere can hold more water than cold one. So this could explain the increased duration in mesoscale convective systems, as well as the rain that is associated with them. The other thing is that these systems during the spring season here, they are a part of the global water cycle, which is accelerating, as it has been reported by the IPCC latest report. That means evaporation is going faster, rain is going faster, and the whole global water cycle is accelerated with implications to regional scale climate. So now, for example, here, what are the challenges? It's important to know what we still need to know about mesoscale convective systems. The main challenge comes from the fact that they are short-lasting weather events, less than 2 days, for example, and they are very difficult to be represented in numerical models, even at very high resolution. We have many papers trying to get the right convection at the right place and time, and this is still challenging, which make it also very challenging even more for the global climate models that are used for climate projections. And in those, actually, mesoscale convective systems are not accounted for. Our results suggested that such extreme events may be more impactful in a warming world, so this also put pressure on the need to represent them well in numerical models. On the other hand, arid regions can benefit from this increase in trends, duration and rain both. And also, another interesting aspect is to know what would be the fate or the state of mesoscale convective systems in the future under a warmer climate. That was all for me to talk about my presentation. And now I will be happy to take questions and discuss with all the attendees. Thank you.
Thank you so much, Dr. Diana, for sharing this interesting work. I can already see so many parallels between both of your presentations, and I'm sure you both have questions for each other, but let us first take some questions from the audience. My first question will go to Professor Taha. So Diana spoke a little bit about how high temperatures or a warmer climate can hold more water vapor. But here the question is more in relation to your study on the surface measurements of rainfall. So with the high temperatures over the UAE, saying that a large fraction of generated rainfall through cloud base is already subject to evaporation before it even reaches the ground. And this is sometimes referred to as virga. So do you expect virga to influence the outcomes of your study, which was exclusively based on surface rainfall measurements?
Yeah, absolutely. But I think we need to keep in mind the whole panoply of variables that influence the results. I mean, first of all, I would love to extend the analysis. We did the work in 2014. We have a number of years since, and these models have a parsimony problem, which means that when you start introducing additional covariates, in this case the climate oscillation indices, you have models that have a lot of parameters. And if you don't have a long sequence, then the quality of the estimates for these parameters is not very good. The more data you have, the better the quality of the model. So we would benefit from redoing the analysis with the last years, and that will allow us to integrate more covariates and model directly their impacts. So there are a number of things that would be interesting. Definitely, yes, but I would integrate also all kinds of other information. Climate oscillation indices themselves are evolving in time. Okay, we have a lot of autocorrelation. We have clear cycles in El Nino or all the indices, and that's what makes them easy to predict and makes them good predictors, but they're going also through trends themselves. That would be something that would be important to integrate. So the short answer is yes, but we need to have enough data to integrate more information to make the model speak, basically.
Indeed, indeed. And even if you were to integrate Virga into the equation, that comes with its own set of uncertainty, which you'd introduce in the model as well.
Absolutely. So one thing we need to do is model the uncertainty associated with these models. It's good to say that the trend is increasing, but if your uncertainty is so large, it basically within your confidence interval, there could be a decreasing trend. So we need to do that. And I didn't want to present work about the uncertainty over here, but that's one of the things that we're working on. There is a paper that was published in 2020 on the uncertainty associated with stationary and non-stationary models with application to the UAE.
Perfect. Thanks a lot, Dr. Taha. My next one goes to Dr. Diana. He's asking, do you expect to see an increase in the Arabian Peninsula's annual rainfall amounts over the next decade? And how does climate change come into play? I think you already wanted to elaborate more on this point.
Yeah, thank you, Dr. I think there are a few things to take into account when trying to answer this question. First of all, we already know that in the tropics and subtropics, there are signs of increasing rainfall. And this was actually predicted even in the fifth report of the IPCC, where some regions were too dry under warmer climate and others were to become more, to experience more rainfall. I would expect that the rain will be increasing, and this for different reasons. First of all, the impact of the expansion of the tropics that we are noticing, meaning that the tropics are stretching more to the north and to the south due to the increase in water vapor in the atmosphere itself, which is related again to the warmer atmosphere that now we have. The second thing is changes that are related to the melting of the ice in the Arctic. It may seem very far from us, but actually it impacts the circulation, mainly the polar jet and its interaction with the subtropical jet. So we have evidence that now the polar jet is becoming slower due to the decrease in temperature gradient between the polar region and the mid-latitude. So once we have a polar jet that is slow, that means we have more intrusion of troughs and more disturbances from mid-latitudes toward our region. And this will impact actually the rain during winter and spring, as we showed in our. So I think on an annual basis, you will have we could expect increase in rain during summer due to the expansion of the tropics and the convection in the tropics. And during fall and winter, we could expect also increase in rain due to the changes in the circulation at mid-latitudes.
Okay. Thanks a lot. Back to Professor Taha. The question is, can the trend analysis and change point detection approaches that you showed in your presentation be used to quantify the impacts of cloud seeding operations on natural rainfall amounts? And if you think so, what would some of the challenges be, and of course the underlying assumptions with that? I know you spoke a lot about uncertainty, but maybe you can throw in a bit more on that.
Yeah, this is a very good question, actually, because what we're observing integrates also the impact of cloud seeding activities. So the series that we're observing, the last part of it takes place during cloud seeding activities. So what we observe is that since cloud seeding activity started, we have an increasing trend in precipitation. But which part of that trend is related to the natural cycle of precipitation, and which part is due to human activities? that leads us to a whole other type of analysis, because correlation is not sufficient. You can have a correlation between two variables, but that doesn't mean that there is causality between them, that one leads to the other. So here we need to go to other type of approaches, what we call fingerprinting techniques, which have been used, for instance, to separate the natural climate change signal from has been induced by human activities in a few papers. And we need to use those approaches now to go and separate that increase in precipitation, which part of it is due to cloud seeding activities and which part is a natural cycle. And that work hasn't been done. So the answer is yes, it can be done. We should have enough data to get some reliable answers, but that work has not been done.
All right. A follow-on question to Dr. Diana, to your earlier response. So you said the total annual rainfall generally over the Arabian Peninsula is projected to increase with climate change. But what does that mean for the intensity of individual events? So will we see a more increase in intensity of individual events, or is this impacting the number of these events? So what implications for flooding and stuff like that, maybe?
Yeah, unfortunately, yes. I think we need to be prepared to more extreme events. This again was the conclusion of the IPCC report for our region and for other regions as well. But I mean, we need to be positive. In my perspective, we need to be positive about this change and try to benefit from it. Whereas in other countries, it could be very, very detrimental for the life of people, and like we saw in Europe, the extreme flooding of this summer. For the UAE and the Arabian Peninsula and arid regions in general, it should be considered as an advantage and adapt the infrastructure of the country to benefit from this precious rain.
Indeed. There's a lot of interest now in managed aquifer recharge in the region here, as you know. So a lot of interest in rainwater harvesting technology, and I think we really need to start looking at that seriously to reap the benefits. Professor Taha, I was personally really interested in your point on the variability in climate indices and their sort of out-of-phase interactions, which might be mistaken for climate change impacts from our warming planet. Just moving forward, what are some ways you suggest we can ensure that these two factors are somewhat decoupled in our long-term forecast when we talk about climate change?
Well, the most important thing is to keep monitoring. Our stations, our data is worth gold, basically, and we need to protect those stations. We need to intensify our monitoring activities. You can't make bricks without clay. That's a sentence that Sherlock Holmes said, basically. You can't predict, you can't do any analysis if you don't have the right data. So we need to intensify our monitoring activities. And with the amount of data that's being collected now in the UAE, I think we're starting to have enough information if we integrate all sources of data, but there is a framework to do that. We can do that in a Bayesian framework fairly efficiently. We can integrate all sources of information to really push our analyses about these questions that you're raising. We have already at least a cycle of even the multi-decadal indices, the longest phases, okay? So ideally, we want to have a couple of cycles, but we already have enough data now to do more sophisticated analyses. We need to put our efforts into it.
Well, I mean, you really hit my next question head on, Professor Taha, because the next question came just now, and it's asking, and I think both of you, of course, can feel free to comment on it. Would you both support setting up a regional scale climatological monitoring network over the Arabian Peninsula? So sort of a regional scale monitoring network. And what are some of the incentives we can offer to policymakers for them to support better coordination between weather services across the region here?
Go ahead, Dr. Diana.
Yeah, this is excellent, idea. Because as Dr. Taha said, we need sustained and long-term data to build on it, especially for sensitive questions such as the impact of climate change on this or that. So a single point is very difficult to rely on. And it's really a good idea if we can get to a network that cover all the region and that is maintained and up to the standards and can be relied on to have the trends over our region. Yeah, I know now it's very segregated by countries or by even institutions sometimes. So as motivation for the policymakers or the decision makers to set this is, we will all be affected by whatever change will happen in the region. Let's say that the flooding or the weather system will not stop at any border. It's something that common. We are under the same sky, so we should be prepared. And as I said, the trends in precipitation could also be used as motivation to have these data. Because if, for example, we have a robust data network, we can build on this to predict the flooding, the amount of rainfall that will fall in this region or in this area, and then based on that, this information can be communicated to municipalities, to ministries that are in charge of the urban design, the infrastructure, and in the countries in the region.
Yeah, I don't know if I have something to add, honestly. Dr. Diana, I think, provided the full answer. Nature does not recognize the frontiers. And by putting all the data, by sharing data, by putting all the data under the same roof, we can do better analysis, more precise and more sophisticated analysis. So the answer is definitely it's a positive. It would be a positive thing, yeah.
Great, and I just maybe can say that both your presentations are actually just firsthand testimonies on the importance of having this monitoring, just to better understand our climate here in the region, which is indeed very complex. Yeah, I mean, there's one open-ended question, but before that, maybe Taha, if you have any specific questions, Diana on her work, or Diana, if you want to have any questions for Taha, please go ahead.
I would love, yes, I have Dr. Taha. So do you have a plan to extend your analysis to recent years?
I would love to. That's why I'm here. I want to maintain the link with the group of friends I have in the UAE, and there are interesting analyses that need to be done. I hope we're going to get to work on this together. So the answer is yes. Definitely the pandemic affected our work and our capacity to see each other and communicate and all, but hopefully now things are going to be improving, and I'm looking forward to working with you, hopefully in the near future.
That's great.
Yeah. So I have a number of questions for Dr. Diana, but I don't want to keep people here till tomorrow morning. So we'll speak about this outside of the webinar framework. Yeah.
Well, now I have to force you to acknowledge this webinar session if you ever publish together and do future work together.
Definitely.
So just to leave everybody with an open-ended question before we just wrap up. Do you both agree that there's about the general statement that wetter places will get wetter and drier places will get drier in our current understanding of where we're going in terms of climate change? Taha, you can go first if you'd like.
Well, that is the consensus globally, but you can't generalize. There are microclimates, there are things that are happening at local scale. There are a whole bunch of activities that take place at a local scale. If we're doing cloud seeding activities in the UAE, for instance, basically that's going to increase the amount of rain in the UAE. And that's a local phenomenon, a local consequence. So yeah, the consensus is globally the ones that caused climate change are not the ones that are suffering from it, and dry places will get drier. But I think we need more refined analyses to understand what's going on.
Go ahead, Dr. Diana.
Yeah, I think Dr. Taha covered very well. We until now we have maybe the first signs, but could be also some variability, or but we will need certainly to investigate this more in depth to really make a statement about it.
All right. Well, thank you very much to both my distinguished speakers that joined me today. It was really a pleasure listening to both of you and sharing your research with us. Thanks to our audience, and whoever missed the webinar can, of course, watch it on our uaerep.ae website. It will be archived there. And yeah, please stay tuned for our third webinar coming soon. Thank you very much, everybody.